Section 6.4 Binomial Coefficients and Combinatorial Identities. Let A and B be real numbers. We want to expand A plus B to the power 2. Everybody knows how to do that, but here we'll do it this way. This means A plus B times A plus B, and we have to multiply a term from the first factor, which is either A or B, with a term from the second factor. And we end up with these four terms. In order to obtain a term with one A and one B, that is these two terms here in the middle, we select one of the factors A plus B, either the first one or the second one, from which we use B, and we use A from the remaining factor. There are two choices to select one of two objects, so two ways, and we have two terms of this kind, these two terms in the middle. So the expression is A squared plus, the expansion is A squared plus 2 choose 1 AB plus B squared. And then we do this for A plus B cubed. It means this, and then again a term from the first factor times a term from the second factor times a term from the third factor. We end up with these terms. Collecting like terms, we obtain this expansion. We will find the coefficients, the coefficient of A squared B directly without doing this expansion explicitly. In order to obtain a term with exactly one B, we select one of the factors A plus B, from which we use B, and we use A from the remaining factors A plus B. This can be done in 3 choose 1, which is 3 different ways. Similarly, A BB plus B AB plus BBA has 3 choose 2, which is 3 different terms. And we end up with this formula, which is, of course, the previous one. We can write the expansion of A plus B cubed using sigma notation this way. Recall that n choose j is equal to n factorial over n minus j factorial times j factorial. And this is another way of writing the same binomial coefficient. Generalizing what we did for 3, we can prove this theorem, binomial theorem, which produces the expansion of A plus B to the n, where n is a positive integer. Example, find the coefficient of A squared B in the expansion of A plus B to the power 6. The term is 6 choose 4, A squared B to the 4, and the coefficient is 6 choose 4, replacing here n and j with 6 and 4, we get this, and the result is 15. Corollary, the sum of these binomial coefficients and choose k, where k varies from 0 to n, is equal to 2 to the n. The proof of this corollary can be obtained from the theorem. Here a and b are any real numbers. We can select a and b to be ones. Then the left hand side is 2 to the n, and the right hand side is just the sum. Problem. Show that n choose k is equal to n choose n minus k. N choose k One way of proving this is to use the formula for n choose k. If you apply the formula n factorial over n minus k factorial times k factorial, and then apply the formula for n choose n minus k, you end up with the same quotient, n factorial over k factorial times n minus k factorial. Theorem, Pascal identity. N plus 1 choose k is equal to n choose k minus 1 plus n choose k for any k between 1 and 10. Proof. We'll consider combinatorial proof here. Let T be a set with n plus 1 elements and A be an element from T. The number of k element subsets of T is n plus 1 choose k. This is from the definition of the binomial coefficient. Now we count the same subsets by splitting them into cases, two classes. There are n choose k minus 1 subsets that contain A, and there are n choose k subsets that do not contain A. Now we apply the addition principle. Because these two classes of subsets are disjoint, the sum of these two numbers is equal to n plus 1 choose k. Pascal triangle, we place the binomial coefficients this way. This is n choose 0 when n is 1. This is n choose 1. In the next row, we have 2 choose 0, 2 choose 1, 2 choose 2. Then in the third row, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. The previous theorem says that the sum of these two numbers is equal to the number in the next row between them. 2 plus 1 is 3, and it continues like that. The end numbers are 0 and 1s, and for any n choose 0 is 1, and n choose n is 1. So we know the end lines, they are 1s, and the lines, the numbers in the middle, any number that is not the n line, is equal to the two numbers place on the previous row next to him, next to it. 10 is 4 plus 6, 20 is 10 plus 10, and so on. Pascal triangle, this is useful when we want to write the expansion, like this one in problem 7, in this problem, a plus b to the 7. We need the next row of the Pascal triangle. Using the 6th row, we write it immediately, and then we use those coefficients to write the expansion. A to the 7 plus the next term is a to the 6b, and the coefficient comes from the next row of the Pascal triangle. 1 plus 6 is 7. The next term is a to the 5th b squared. The exponent of a decreases by 1. The exponent of b increases by 1. And the next coefficient is 6 plus 15, 21. And we continue like that. The next problem. What is the coefficient of x to the 9 of the expansion of 2 minus x to the power 19? 2 minus x is the same as 2 plus negative x. So we obtain this. 19 choose 9, 2 to the 10, negative x to the power 9. And then for 19 choose 9, we use the formula. (19) factorial over 19 minus 9, which is 10 factorial, times 9 factorial in the denominator. 2 to the 10 comes from here. And we get this result. Problem. Prove that if k is between 1 and 10, positive integer, k times n choose k is equal to n times n minus 1 choose k minus 1 using combinatorial proof. And we have this hint. Show that the two sides of the identity count the number of ways to select a subset with k elements from a set with n elements, and then an element from this subset. A subset with k elements from a set with n elements can be selected in n choose k different ways, and then from that set we select one element in k choose 1 different ways, and k choose 1 is just k. So this is the left hand side. Now count. We can count how we can obtain the same selection in different way. First select one element, and then select n minus 1 additional elements to form a k element subset that contains the selected element. From n elements, one element can be selected in n choose 1, which is n, different ways, and then from the remaining n minus 1 elements, we select k minus 1 elements in n minus 1 choose k minus 1 different ways. And this is just the right hand side. The multiplication principle provides the right hand side. So both sides must be equal.